On July the 2nd, 1967, at precisely 1419 UTC, a pair of American satellites detected something that shouldn't have existed. The Vela 3 and Vela 4 spacecraft, orbiting some 118,000 kilometers above the Earth, registered a sudden flash of gamma radiation that didn't match anything in their extensive database of nuclear weapon signatures. The satellites had been designed for one purpose, and one purpose only: to catch the Soviet Union cheating on the Partial Test Ban Treaty by detonating nuclear weapons in space. Instead, they stumbled upon evidence of the most violent explosions in the known universe. Explosions so powerful that they make nuclear weapons look like party poppers. Explosions that, under the wrong circumstances, could sterilize entire planets. But nobody knew any of that yet. In 1967, the scientists at Los Alamos simply filed the anomaly away and moved on with their day. After all, whatever it was, it clearly wasn't a Soviet nuke, and that was the only thing they were being paid to worry about. It would take another 6 years before anyone bothered to tell the rest of the world what the Vela satellites had found. And it would take another 3 decades before we finally understood what we were looking at. This is the story of gamma ray bursts, the most energetic phenomena in the universe since the Big Bang itself, and what would happen if one of them were ever pointed directly at Earth. Spoiler alert, it wouldn't be great. To understand how we accidentally discovered cosmic death rays while looking for Soviet nuclear tests, we need to go back to the early 1960s and the absolutely batshit insane period of history known as the Cold War. By 1963, both the United States and the Soviet Union had conducted hundreds of nuclear weapons tests, and the world was getting a little nervous about all the radioactive fallout drifting through the atmosphere. So, on August 5th, 1963, the two superpowers, along with the United Kingdom, signed the Partial Test Ban Treaty, which prohibited nuclear weapons tests in the atmosphere, in outer space, and underwater. Underground tests were still fair game, presumably because irradiating your own territory was considered a matter of national sovereignty. Now, the thing about treaties is that they only work if everyone actually follows them. And the thing about the Soviet Union was that the United States didn't exactly trust them to follow anything. So the Americans needed a way to verify compliance, which is a diplomatic way of saying they needed to catch the Soviets in the act if they decided to cheat. Ground-based detection systems could pick up atmospheric tests reasonably well, but space-based detonations were a different story. If the Soviets wanted to test a nuclear weapon in orbit, or even behind the moon where no one could see it, they could theoretically do so without anyone on Earth being the wiser. Unless, of course, someone put detection satellites in space to watch for the telltale signatures of nuclear explosions. Enter Project Vela, named after the Spanish verb meaning to watch or to keep vigil. The project was a joint effort between the United States Atomic Energy Commission and the Department of Defense, with the goal of developing space-based sensors capable of detecting nuclear detonations anywhere in near-Earth space. The first pair of Vela Hotel satellites launched on October 17, 1963, just 1 week after the Partial Test Ban Treaty went into effect. The timing was not a coincidence. These early satellites were relatively simple affairs, equipped with 12 external X-ray detectors and 18 internal neutron and gamma-ray detectors, powered by solar panels generating about 90 watts. They were designed to detect the characteristic signatures of nuclear explosions: the initial flash of X-rays, the burst of gamma radiation, and the spray of neutrons that accompany any nuclear detonation. A nuclear bomb going off in space produces a very specific pattern. First, there's an incredibly intense flash of X-rays that lasts less than a millionth of a second. Then, the gamma radiation spikes and begins to decay in a predictable curve as the radioactive byproducts of the explosion break down. If you know what you're looking for, a nuclear detonation is essentially unmistakable. The Vela satellites were launched in pairs, placed in nearly circular orbits about 118,000 kilometers from Earth, which is roughly one-third of the distance to the Moon. This altitude was chosen for several reasons. First, it kept the satellites well above the Van Allen radiation belts, which would have created too much background noise in the sensors. Second, the high orbit meant that no part of the Earth was ever shielded from direct observation. And third, by positioning two satellites on opposite sides of their orbit, they could detect signals from any direction, including from behind the Moon, where the Soviets might try to hide a clandestine test. The early Vela satellites had a design life of 6 months, but they actually kept functioning for 5 years before being shut down. As the program continued, more advanced satellites were developed and launched. The Advanced Vela series, which began launching in 1967, included additional instruments like bang meters, which were silicon photodiode sensors designed to detect the characteristic double flash of an atmospheric nuclear explosion. These newer satellites consumed about 120 watts of power and could determine the location of a nuclear detonation to within about 3,000 miles. By 1967, the Vela program had become remarkably sophisticated. The satellites could detect not just the initial flash of a nuclear explosion, but also the expanding cloud of radioactive debris that would follow. Even if someone tried to shield the initial blast from view by detonating a weapon behind the Moon, the gamma-ray detectors would eventually pick up the radiation from the expanding debris cloud as it moved into the satellite's line of sight. And then, on that fateful day in July 1967, the Vela satellites detected something that wasn't in any of their reference databases. The signal had all the hallmarks of high-energy radiation from space, but it didn't look anything like a nuclear weapon. Nuclear bombs produce a very brief, very intense burst of gamma rays that lasts less than a millionth of a second, followed by a gradual decay as unstable nuclei break down. The signal detected on July 2nd had neither of these characteristics. Instead, it showed two distinct peaks in the light curve, with the radiation intensity rising and falling in a pattern that simply made no sense for any known nuclear device. Ray Klebezadel, a physicist at Los Alamos Scientific Laboratory who had taken over responsibility for the gamma-ray instruments on the Vela satellites in 1965, looked at the data and immediately recognized that whatever this was, it wasn't a bomb. The signature was completely wrong. But if it wasn't a nuclear weapon, what was it? A solar flare, perhaps. Klebezadel checked the records. No solar activity had been reported on that day. Some kind of equipment malfunction. The signal had been detected by multiple satellites simultaneously, which ruled out a single instrument glitch. For the moment, there was no obvious explanation, and since the signal clearly wasn't a threat to national security, Klebezadel simply filed it away for future investigation and moved on to more pressing matters. But the mysterious signals kept coming. As additional Vela satellites were launched with better instruments, the Los Alamos team continued to find inexplicable bursts of gamma radiation in their data. Vela 5, launched in May 1969, had significantly improved sensitivity and time resolution compared to the earlier satellites. And sure enough, it detected more of these strange events. Vela 6, launched in April 1970, was specifically designed to help determine the direction from which the gamma rays were arriving. By spacing the Vela 6 satellites as far apart as possible from the Vela 5 pair, sometimes on the order of 10,000 kilometers, the team could use the slight differences in arrival time at each satellite to triangulate the source of the radiation. Gamma rays travel at the speed of light, which is very fast indeed, but not infinitely fast. A signal arriving from a particular direction in space would reach the closer satellite a tiny fraction of a second before it reached the farther one. By carefully measuring these time differences across multiple satellites, Klebesattel and his colleagues were able to determine rough estimates for the positions in the sky from which 16 separate bursts had originated. In 1969, while preparing for the launch of Vela 5, Klebesattel and his colleague Roy Olsen went back through the older Vela 4 data and found that signal from July 2, 1967, which had also triggered the still operational Vela 3 satellites. This appears to have been the first gamma-ray burst ever recorded by human instruments, though the constellation of satellites at the time didn't have sufficient timing resolution to pinpoint its location. In retrospect, Klebesattel would later identify this event as the first observed gamma-ray burst in history. The time history of this burst was later reconstructed and published in Scientific American in October 1976. No earlier observation of a similar event has ever been found. By 1972, the Los Alamos team had accumulated enough data to draw some important conclusions. Ian Strong, another scientist at the laboratory, was asked to conduct a systematic analysis of Klebesattel's growing collection of gamma-ray anomalies. Using the timing data from the later Vela satellites, Strong, Klebesattel, and Olsen were able to determine the approximate directions to 16 separate bursts. What they found was startling. The bursts were scattered randomly across the sky. They weren't clustered along the plane of the Milky Way, as they would be if they came from within our galaxy. They weren't concentrated around the sun or the moon or any of the planets. They weren't coming from any known astronomical source. Whatever these things were, they appeared to be of cosmic origin, coming from somewhere far beyond the solar system. In 1973, 6 years after the first detection, Klebesattel, Strong, and Olsen finally published their findings in a paper titled Observations of Gamma-Ray Bursts of Cosmic Origin in the Astrophysical Journal Letters. The paper was modest in its claims, simply reporting the detection of 16 bursts of gamma radiation that could not be attributed to any known source and appeared to originate from somewhere outside the solar system. The authors were careful not to speculate too wildly about what might be causing these bursts, though they did note that the energy involved must be substantial given the apparent distances. The reaction from the astronomical community was immediate and intense. Here was an entirely new phenomenon, detected not by astronomers but by military satellites looking for Soviet nuclear tests. Nobody had predicted it. Nobody had any idea what could be causing it, and nobody could agree on where the bursts were actually coming from. Within a few years, more than 200 different theoretical models had been proposed to explain gamma-ray bursts. Some scientists suggested they might be caused by collisions between comets and neutron stars. Others proposed that they were produced by antimatter meteors hitting the sun. Still, others speculated about alien civilizations, exotic forms of matter, or entirely new physics that had yet to be discovered. The problem was that almost any theory could fit the available data because there was so little data to work with. The fundamental question that divided the scientific community was simple in principle, but maddeningly difficult to answer in practice. Were these bursts coming from relatively nearby within our own Milky Way galaxy, or were they coming from incredibly far away from other galaxies entirely? This distinction mattered enormously because of what it implied about the energy involved. If gamma-ray bursts were local phenomena occurring within a few hundred or thousand light-years of Earth, then the amount of energy required to produce the observed signals would be large, but not unreasonable. A moderately powerful explosion at close range can produce a bright flash. But if the bursts were extragalactic, originating billions of light-years away, then the energy involved would have to be almost incomprehensibly vast. To appear as bright as they did from such enormous distances, the explosions would have to be releasing more energy in a few seconds than our Sun will produce in its entire 10 billion-year lifetime. The very notion seemed absurd. What kind of cosmic event could possibly generate that much energy? The key to answering this question lay in the distribution of bursts across the sky. If gamma-ray bursts were coming from within the Milky Way, they should show some concentration toward the galactic plane, the flat disk of stars that makes up most of our galaxy. After all, that's where most of the stars and potential burst sources would be located. But the Vela data showed no such concentration. The bursts appeared to be distributed randomly or isotropically across the entire sky. This isotropy was strong evidence against a galactic origin, though not quite definitive. Some models of the Milky Way could still produce an isotropic distribution if the sources were located in a large spherical halo surrounding the galaxy rather than in the disk itself. To settle the debate, astronomers needed more data, better instruments, and, ideally, some way to connect gamma-ray bursts with objects visible at other wavelengths. If they could identify a galaxy or a star at the same location as a burst, they could measure its distance directly and, finally, answer the question of whether these explosions were local or cosmic. Throughout the 1970s and 1980s, astronomers searched desperately for counterparts to gamma-ray bursts at other wavelengths. Every time a burst was detected, they would point optical telescopes, radio telescopes, and X-ray satellites at the estimated position to look for anything unusual. The results were consistently disappointing. Either the positions determined from the gamma-ray satellites were too imprecise to identify a unique source, or there simply was nothing to see. In some cases, where the burst positions were determined with unusual accuracy, the locations contained nothing but faint, unremarkable stars and galaxies. This was actually important information. The absence of bright counterparts meant that whatever was producing gamma-ray bursts either involved very faint objects or was located very far away. But it didn't help resolve the debate between the local and cosmological models. One major step forward came with the establishment of the Interplanetary Network, or IPN, in the late 1970s. The idea was simple but powerful. Instead of relying solely on satellites orbiting Earth, the network incorporated gamma-ray detectors on spacecraft throughout the solar system. By the end of 1978, the network included the Russian Prognoz 7 satellite in Earth orbit, the German Helios 2 spacecraft in orbit around the Sun, and NASA's Pioneer Venus orbiter, along with the Soviet Venera 11 and Venera 12 missions at Venus. With detectors spread across millions of kilometers of space, the timing differences between burst detections became much larger and much easier to measure. This allowed astronomers to pinpoint the locations of some bursts with unprecedented accuracy, sometimes narrowing down the source to just a few arc-minutes of sky. But even these improved positions failed to reveal obvious counterparts. The galaxies visible in the burst error boxes were faint and distant, consistent with the cosmological model, but not definitively proving it. The debate continued. The real breakthrough came in 1991 with the launch of the Compton Gamma Ray Observatory, one of NASA's great observatories. Compton carried an instrument called BATSI, the Burst and Transient Source Explorer, which was specifically designed to detect and localize gamma-ray bursts. Over its 9-year mission, BATSI would detect nearly 3,000 bursts, more than all previous missions combined. The results were unambiguous. BATSI confirmed what the Vela satellites had first suggested. Gamma-ray bursts are distributed uniformly across the sky, with no concentration toward the galactic plane, the galactic center, or any other structure in the Milky Way. The isotropy was essentially perfect. This dealt a severe blow to the galactic models. If gamma-ray bursts were coming from within our galaxy, they would have to be located in an almost perfectly spherical halo, with the Sun sitting precisely at the center. This seemed like an absurd coincidence. Why would the Sun, a perfectly ordinary star in the outskirts of the Milky Way, happen to be at the exact center of a distribution of exotic, high-energy sources? The cosmological model, by contrast, naturally predicted an isotropic distribution. If the bursts were coming from all directions in the distant universe, with no preference for any particular direction, then of course they would appear uniform across the sky. We don't occupy any special position in the cosmos, but the BATSI results, as compelling as they were, still didn't provide direct proof of cosmological distances. For that, astronomers needed to catch a burst in the act and measure the distance to its source. This required detecting the burst with enough precision to identify its host galaxy, and then measuring the redshift of that galaxy to determine how far away it was. The problem was speed. Gamma-ray bursts are fleeting events, typically lasting anywhere from a fraction of a second to a few minutes. By the hour, time astronomers could determine a burst's position from the gamma-ray data, slew an optical telescope to that location, and take an exposure deep enough to see anything interesting. The burst and any associated optical emission had usually faded below detectability. What was needed was a satellite that could detect a burst, determine its position, and alert ground-based telescopes all within minutes rather than hours or days. Enter Beppo-Sachs, an Italian-Dutch X-ray astronomy satellite launched in April 1996. While not designed specifically for gamma-ray burst science, Beppo-Sachs had a crucial capability that previous missions lacked. It could detect a burst with its gamma-ray monitors, then quickly slew its more precise X-ray telescope to the burst location to look for fading afterglow emission. On February 28, 1997, Beppo-Sachs detected a gamma-ray burst designated GRB 970228, and for the first time managed to catch the X-ray afterglow. Within hours, ground-based telescopes were pointed at the position and detected a fading optical source. This was the first time anyone had ever seen a gamma-ray burst at wavelengths other than gamma rays and X-rays. It was a watershed moment in the field. When the optical afterglow faded, deep imaging revealed a faint, distant galaxy at the same location. The burst had occurred in that galaxy, which meant it had to be extragalactic. The cosmological model was right. Gamma-ray bursts were coming from billions of light-years away, which meant they were releasing almost unimaginable amounts of energy. The case was strengthened even further by the next major burst detected by Beppo-Sachs. On May 8, 1997, the satellite detected GRB 9705-8, and this time the response was even faster. Within 4 hours of the burst, research teams were making observations across multiple wavelengths. The optical afterglow was bright enough that astronomers could take spectra, spreading the light out into its component wavelengths to look for the characteristic absorption lines that would reveal the object's redshift and thus its distance. The result was stunning. GRB 97058 was located at a redshift of at least 0.835, corresponding to a distance of roughly 6 billion light-years. The burst had released more energy in a few seconds than a typical supernova releases in weeks. The cosmological model was now confirmed beyond any reasonable doubt. Gamma-ray bursts were indeed the most energetic explosions in the universe, releasing in seconds what the Sun would take 10 billion years to produce. The question was no longer whether these events were cosmological, but what on Earth, or rather what not on Earth, could possibly produce such phenomenal amounts of energy. The discovery of afterglows transformed the field overnight. Suddenly, astronomers could study gamma-ray bursts using the full range of their instruments, from radio telescopes to optical observatories to X-ray satellites. Each new burst became an opportunity to learn more about these extraordinary events. And what they learned was both fascinating and terrifying. First, they discovered that gamma-ray bursts come in two distinct flavors. Some bursts are long, lasting anywhere from a few seconds to several minutes, with complex light curves showing multiple peaks and valleys. Others are short, lasting less than 2 seconds, and often consisting of just a single spike of emission. The two types have different spectral characteristics as well, with short bursts tending to have harder, more energetic spectra than long bursts. This division, first clearly established by Batsy observations, suggested that the two types of bursts might have different origins. Whatever was producing the long bursts might not be the same thing producing the short ones. Second, astronomers found that long gamma-ray bursts are associated with a particular type of galaxy. Small, irregular galaxies with active star formation. This was an important clue. Star formation produces massive stars, and massive stars die young, often in spectacular explosions. The association with star-forming galaxies suggested that long bursts might be related to the deaths of massive stars. This suspicion was dramatically confirmed in 1998 when the gamma-ray burst GRB 980425 was found to coincide with a supernova explosion in a nearby galaxy. The supernova, designated SN 1998BW, was unusual, much more energetic than typical supernova, with material expanding at velocities approaching 10% of the speed of light. It was what astronomers would come to call a hypernova, a supernova, the death throes of an extremely massive star. The connection between long gamma-ray bursts and hypernova became even clearer with the detection of GRB 030329 in March 2003. This burst, one of the closest and brightest ever observed, was followed by an unmistakable supernova signature in its optical afterglow. The spectrum showed the characteristic features of a type Ike supernova, a type of stellar explosion in which a massive star has been stripped of its outer hydrogen and helium layers before exploding. This was the smoking gun. Long gamma-ray bursts were being produced by the deaths of massive stars, but not just any deaths. They required a particular type of progenitor, a rapidly rotating star that had lost its outer envelope, collapsing to form a black hole while shooting jets of material out along its rotation axis at velocities approaching the speed of light. The model that emerged to explain long gamma-ray bursts is called the collapsar model, first proposed by astrophysicist Stan Woosley of the University of California, Santa Cruz. In this model, the progenitor is an extremely massive star, perhaps 30 or more times the mass of the Sun, that has reached the end of its nuclear burning life. Like all stars, it has been sustained throughout its existence by the energy released from nuclear fusion in its core. Hydrogen fuses to form helium. Helium fuses to form carbon. Carbon fuses to form heavier elements, all the way up to iron. But iron is the end of the line. Unlike lighter elements, fusing iron doesn't release energy, it consumes it. Once a massive star develops an iron core, there's no longer any source of energy to support the star against its own gravity. The core collapses catastrophically in about a second, from roughly the size of the Earth to a ball perhaps 20 kilometers across. For most massive stars, this collapse is halted when the core reaches nuclear densities, triggering a bounce and a supernova explosion that blows the star apart while leaving behind a neutron star at the center. But if the star is massive enough, even the neutron degeneracy pressure that supports a neutron star cannot withstand the crushing force of gravity. The collapse continues, and the core disappears behind an event horizon to form a black hole. But here's where it gets interesting. If the collapsing star is rotating rapidly, the material falling toward the newly formed black hole doesn't fall straight in. Instead, it swirls into an accretion disk, a disk of superheated matter spiraling around the black hole like water going down a drain. As material from this disk falls into the black hole, an enormous amount of gravitational energy is released. Some of this energy goes into heating the disk, but a significant fraction is channeled into two powerful jets of material that shoot outward along the rotation axis of the black hole. These jets travel at velocities exceeding 99.9% of the speed of light, punching through the outer layers of the dying star like blowtorches through butter. When the jets finally break through the stellar surface and emerge into space, they emit an intense burst of gamma radiation. This is the gamma ray burst we detect. The burst itself lasts only as long as the jets remain active, typically a few seconds to a few minutes, after which the central engine shuts down and the afterglow begins to fade. The collapsar model explained many of the observed properties of long gamma ray bursts. It explained why they were associated with star-forming galaxies, since massive stars are short-lived and die close to where they were born. It explained the connection to hypernovae, since the same event that produces the gamma ray burst also disrupts the star and creates the supernova explosion. And it explained one of the most puzzling aspects of gamma ray bursts, their apparently impossible energy output. You see, when astronomers first calculated how much energy a gamma ray burst would have to release to appear as bright as it did from billions of light years away, they assumed the explosion was spherical, radiating equally in all directions. This assumption led to energy estimates that seemed physically impossible, equivalent to converting the entire mass of a star into pure radiation instantaneously. But the collapsar model revealed that gamma ray bursts are anything but spherical. The emission is concentrated into two narrow jets, each one pointing in a different direction. If you happen to be looking down the barrel of one of those jets, the burst appears incredibly bright because all that energy is concentrated in your direction. But if you're viewing the burst from the side, you see much less emission, or perhaps none at all. This beaming effect dramatically reduces the total energy required to produce the observed gamma ray brightness. Instead of radiating energy equally in all directions, the burst is concentrating its output into a cone perhaps 10 or 20 degrees wide. This means the total energy release is perhaps 100 times less than would be required for a spherical explosion. It's still an enormous amount of energy, but it's no longer physically impossible. The beaming also explains why gamma-ray bursts are so rare. We only see a burst if we happen to be within the cone of one of the jets. For every burst we detect, there are many more that are pointing in other directions, invisible to us. Estimates suggest that for every gamma-ray burst we observe, perhaps 100 or more are occurring that we never see because their jets are aimed elsewhere. This has important implications for the rate of gamma-ray bursts in any given galaxy, including our own Milky Way. But the collapsor model only explains long gamma-ray bursts. What about the short ones? Those mysterious flashes lasting less than 2 seconds that make up roughly 30% of the observed population. For years, the origins of short bursts remained a mystery. They weren't associated with supernovae, and they seemed to occur in different types of galaxies than long bursts, including old elliptical galaxies with little or no ongoing star formation. Whatever was producing short bursts, it clearly wasn't the death of a massive star. The leading hypothesis was that short bursts were produced by the merger of 2 neutron stars, or perhaps a neutron star and a black hole. Neutron stars are the compressed cores of massive stars that weren't quite massive enough to collapse into black holes. They pack roughly 1.5 times the mass of the Sun into a sphere perhaps 20 kilometers across, making them the densest objects in the universe that aren't black holes. When 2 neutron stars orbit each other, they gradually spiral inward over millions or billions of years, losing energy to gravitational radiation. Eventually, they get close enough that tidal forces tear them apart, and they merge in a cataclysmic collision that forms a black hole. This process, like the collapsor model, produces an accretion disk and jets, but on a much shorter timescale. The entire merger takes less than a second, producing a brief, intense burst of gamma rays, exactly what's observed in short gamma-ray bursts. For years, this neutron-star merger hypothesis was just that, a hypothesis. There was no direct proof that short gamma-ray bursts were produced by merging neutron stars. The evidence was circumstantial. The association with old stellar populations, the short duration, the lack of associated supernovae. It was compelling but not conclusive. Then came August 17, 2017, and everything changed. On that day, the LIGO and Virgo gravitational wave observatories detected a signal designated NAIWS 0817. Unlike the previous gravitational wave detections, which had all come from merging black holes, this signal had the characteristic signature of 2 neutron stars spiraling together and colliding. The gravitational waves were audible for approximately 100 seconds as the neutron stars completed their final orbits, accelerating from about 12 revolutions per second to over 1,000 before merging. Then, 1.7 seconds after the gravitational wave signal ended, the Fermi Gamma-Ray Burst Monitor and the Integral spacecraft detected a short gamma-ray burst from the same region of sky. The burst was designated GRB 1170817A, and it lasted about 2 seconds, exactly as predicted for a neutron star merger. The coincidence in time and space between the gravitational wave signal and the gamma-ray burst was overwhelming. The probability of detecting both signals from the same location by chance was calculated at roughly 1 in 20 million. This was it. This was the proof that short gamma-ray bursts are produced by merging neutron stars. The gravitational waves told astronomers that 2 neutron stars had merged, and the gamma-ray burst told them what happens when they do. But that wasn't even the most remarkable part of the discovery. Within hours of the gravitational wave and gamma-ray detections, alerts went out to astronomers around the world. Over 70 ground-based and space-based telescopes were pointed at the source location, a region of sky in the constellation Hydra. 11 hours after the merger, optical telescopes detected a new point of light in a galaxy called NGC 49993, located about 130 million light-years from Earth. This was the kilonova, the visible aftermath of the neutron star collision, powered by the radioactive decay of heavy elements forged in the explosion. Over the following days and weeks, the kilonova was observed at wavelengths ranging from ultraviolet through optical and infrared to X-ray and radio. The data confirmed theoretical predictions about what happens when neutron stars merge. The collision produces a hot, dense environment where heavy elements like gold, platinum, and uranium are rapidly synthesized through a process called the R process. Much of the gold in your jewelry and much of the uranium in nuclear reactors was probably created in ancient neutron star mergers like this one. GW Sanzom 817 and GRB 817A represented a turning point not just for gamma-ray burst science, but for astronomy as a whole. For the first time, humans had observed the same cosmic event using both gravitational waves and light, opening the era of multi-messenger astronomy. The detection confirmed the neutron star, merger origin for short gamma-ray bursts, solved a long-standing mystery about the astrophysical source of heavy elements, and provided new tests of fundamental physics. By comparing the arrival times of the gravitational waves and the gamma rays, which had been traveling together for 130 million years, scientists could constrain the difference between the speed of gravity and the speed of light to less than 3 parts in a quadrillion. Einstein's general relativity passed yet another test with flying colors. But amid all the celebration, there was a sobering realization. GRB 170817A was relatively weak as gamma-ray bursts go, between 100 and 1,000,000 times less energetic than typical short bursts at similar distances. This wasn't because the merger was less violent than usual, but because we weren't looking directly down the jet. The burst was observed at an angle of about 30 degrees off axis, which meant we were seeing only the edge of the emission cone. If we had been looking straight down the barrel, the burst would have been far, far brighter. And that brings us to the uncomfortable question that had been lurking in the background ever since the first gamma-ray burst was detected in 1967. If these events are so incredibly energetic, what would happen if one went off close to home? What would happen if a gamma-ray burst occurred within our own Milky Way galaxy, with its jets pointed directly at Earth? The short answer is nothing good. The long answer is considerably more disturbing, and it involves the systematic destruction of Earth's ozone layer, a dramatic increase in cancer-causing ultraviolet radiation reaching the surface, the collapse of the marine food chain, and, possibly, the extinction of a significant fraction of all life on the planet. But that's a story for later. For now, let's just appreciate how far we've come from that first puzzling signal detected by the Vela satellites in July 1967. In little more than 50 years, we've gone from complete ignorance to a fairly detailed understanding of what gamma-ray bursts are, how they're produced, and what they tell us about the most extreme processes in the universe. We know that long bursts are produced by the collapse of massive stars into black holes, and that short bursts are produced by the merger of neutron stars. We know that the energy is channeled into narrow jets, moving at nearly the speed of light, and that we only see the bursts that happen to be pointed in our direction. We know that gamma-ray bursts are cosmological events, occurring in galaxies billions of light-years away, and that they represent the most powerful explosions since the Big Bang itself. But we also know that gamma-ray bursts don't only happen in distant galaxies. They happen everywhere that massive stars die or neutron stars merge, which means they happen in our own Milky Way as well. We've never observed a gamma-ray burst from within our galaxy, which is actually a testament to how rare these events are. Estimates suggest that a galaxy like the Milky Way might experience a gamma-ray burst perhaps once every few million years. But over the 4.5 billion years that Earth has existed, that adds up to potentially thousands of bursts within our galaxy. Most of them would have been pointed in other directions, their deadly jets missing us entirely. But some of them, statistically speaking, must have been aimed at Earth. And some of those must have struck our planet with devastating consequences. Whether any gamma-ray burst has actually caused a mass extinction on Earth is a question we'll explore in detail later in this documentary. The evidence is circumstantial but intriguing. For now, the important point is that gamma-ray bursts are real, they're powerful, and they're not just an abstract phenomenon happening in distant corners of the universe. They're a feature of the cosmos we inhabit, and they may have shaped the history of life on our planet in ways we're only beginning to understand. The story of gamma-ray bursts is, in many ways, a story about the unexpected ways that scientific discoveries happen. Nobody set out to discover cosmic explosions 1 billion times more powerful than supernovae. The Vela satellites were designed to catch Soviet nuclear cheats, not to revolutionize astrophysics. Ray Klebes-Adel and his colleagues at Los Alamos were weapons scientists, not astronomers. And yet, by paying attention to anomalous data that didn't fit their expected patterns, they stumbled upon one of the most important discoveries in 20th century astronomy. It took decades of additional work by scientists around the world using increasingly sophisticated instruments and theoretical models to unravel the mystery of what the Vela satellites had found. And even now, more than 50 years later, there are still aspects of gamma-ray bursts that we don't fully understand. We don't know exactly why some stellar collapses produce gamma-ray bursts, while others don't. We don't know the precise mechanism that converts gravitational energy into the relativistic jets that produce the gamma-ray emission. We don't know how common gamma-ray bursts are in galaxies like our own, or how likely it is that one will occur close enough to affect Earth in the foreseeable future. But we know enough to be concerned. And we know enough to ask the question that this documentary is ultimately about. What would happen if a gamma-ray burst hit Earth? The answer, as we'll see, involves atmospheric chemistry, ultraviolet radiation, mass extinctions, and the uncomfortable realization that we live in a universe that is not designed with our survival in mind. The cosmos is beautiful and majestic and awe-inspiring, but it is also profoundly dangerous, filled with phenomena that could snuff out life on our planet without warning and without mercy. Gamma-ray bursts are perhaps the most extreme example of this cosmic danger. Events so powerful that they can sterilize entire worlds from thousands of light years away. The fact that we're here to ask these questions at all suggests that Earth has been lucky so far. Whether that luck will hold is another matter entirely. Now that we know gamma-ray bursts exist, and that they come in two distinct varieties, the obvious question becomes, what exactly is happening out there to produce such incomprehensible amounts of energy? We've touched on the basic mechanisms already: the collapsor model for long bursts and the neutron star merger model for short bursts. But to truly appreciate what we are dealing with, we need to dive deeper into the physics of these cosmic catastrophes. Because when you start to understand just how violent these events really are, the idea that one might someday affect Earth becomes a lot less abstract and a lot more terrifying. Let's start with long gamma-ray bursts, since they're the more common and better understood of the two types. As we discussed, these are produced by the deaths of massive stars, but not just any massive stars. The progenitors of long gamma-ray bursts are thought to be Wolf-Rayet stars, highly evolved stellar objects that represent the final stage before a massive star's core collapses. Wolf-Rayet stars are monsters by any reasonable standard. They typically started their lives with masses of 25 to perhaps 100 times that of the Sun, and they burn through their nuclear fuel at a prodigious rate. While a star like our Sun will shine steadily for about 10 billion years, a Wolf-Rayet progenitor might exhaust its fuel in just a few million years. These stars are also extraordinarily luminous and hot, with surface temperatures reaching 50,000 Kelvin or more, compared to the Sun's relatively modest 5,800 Kelvin. They're so hot that they don't just shine. They blaze, pumping out intense ultraviolet radiation that would be lethal to any life within a considerable radius. But the most distinctive characteristic of Wolf-Rayet stars is that they're losing mass at a tremendous rate. Powerful stellar winds, driven by the intense radiation pressure at the star's surface, blow material off into space at velocities exceeding 2,000 kilometers per second. Over the course of their brief lives, these stars can shed more than half their original mass, stripping away their outer layers of hydrogen and helium to expose the heavier elements forged in their cores. By the time a Wolf-Rayet star is ready to die, it's been reduced to a bare carbon and oxygen core, perhaps still 10 or 20 times the mass of the Sun, surrounded by nothing but the tenuous remnants of its former envelope. This mass loss is actually crucial for the production of a gamma-ray burst. One of the requirements for the collapsor model is that the jets produced by the collapsing core must be able to punch through the star and emerge into space. If the star still had its full complement of outer layers, the jets might get bogged down and dissipate before they could break free. But a stripped-down Wolf-Rayet star presents a much easier target, allowing the jets to escape and produce the gamma-ray emission we observe. The other crucial requirement is rapid rotation. For a collapsing stellar core to form an accretion disk and launch jets, it needs to be spinning fast. If the core is rotating slowly, the infalling material will simply plunge straight into the newly formed black hole without forming a disk. But if the core has significant angular momentum, the material will be forced into orbit around the black hole, gradually spiraling inward as it loses energy through friction and other processes. This accretion disk is where the action happens. As matter falls from the disk into the black hole, gravitational potential energy is converted into heat and radiation with an efficiency that puts nuclear fusion to shame. Nuclear fusion converts less than 1% of the rest mass of hydrogen into energy. Accretion onto a black hole can convert up to 40% of the infalling mass into energy. This is why gamma-ray bursts can release so much power. They're tapping into the most efficient energy source in the universe. The jets themselves are thought to be launched by magnetic fields threading the accretion disk and the black hole. As the disk rotates and material spirals inward, magnetic field lines get twisted and wound up like rubber bands. Eventually, the magnetic tension becomes so great that the field lines snap outward, accelerating matter along the rotation axis to velocities approaching the speed of light. The process is similar to what happens in quasars and other active galactic nuclei, but compressed into a much shorter timescale and a much smaller volume. The result is two beams of relativistic material shooting out in opposite directions, perpendicular to the plane of the accretion disk, each one carrying an enormous amount of energy concentrated into a narrow cone. These jets have to fight their way through whatever remains of the star's outer layers. Even for a stripped Wolf-Rayet star, this is no trivial task. The jets essentially have to drill a tunnel through stellar material, pushing aside or vaporizing anything in their path. This drilling process takes time, typically several seconds, which is why long gamma-ray bursts last as long as they do. The gamma-ray emission begins only when the jets finally break through the stellar surface and emerge into space. Once the jets are free, they continue to accelerate, reaching what physicists call relativistic velocities, meaning velocities close enough to the speed of light that the effects of special relativity become important. Material in a gamma-ray burst jet is typically moving at 99.9% of the speed of light or faster, corresponding to what's called a Lorentz factor of 10 or more. At these speeds, strange things happen. The mass of the moving material increases, time dilation causes clocks to run slow, and the radiation emitted by the jet is dramatically boosted in the direction of motion through a process called relativistic beaming. This beaming is crucial to understanding why gamma-ray bursts appear so bright. The radiation that would normally be emitted in all directions is instead concentrated into a narrow cone along the direction of the jet's motion. If you are within that cone, looking back toward the source, the burst appears enormously brighter than it would otherwise. If you are outside the cone, you might see only a faint afterglow, or nothing at all. The actual gamma-ray emission is thought to arise from internal shocks within the jet. The central engine, the accreting black hole, doesn't produce a steady outflow of material. Instead, it coughs out blobs or shells of material at slightly different velocities. When a faster shell catches up to a slower one, the collision produces a shock wave that heats the material to extreme temperatures and accelerates electrons to relativistic energies. These accelerated electrons then radiate gamma rays through a process called synchrotron emission, spiraling around magnetic field lines and giving off high-energy photons with each turn. The complex light curves of gamma-ray bursts, with their multiple peaks and valleys, are thought to reflect the irregular activity of the central engine, each pulse corresponding to a new shell collision somewhere in the jet. After the prompt gamma-ray emission ends, the jets continue to plow into the surrounding medium, the interstellar gas and dust that fills the space between stars. This collision produces a second set of shock waves, external shocks, that give rise to the longer-lasting afterglow emission observed at X-ray, optical, infrared, and radio wavelengths. The afterglow can persist for days, weeks, or even months, gradually fading as the blast wave decelerates and the shocked material cools. So that's the collapsar model for long gamma-ray bursts. A rapidly rotating, massive star collapses. Its core forms a black hole surrounded by an accretion disk, and magnetic fields launch relativistic jets that punch through the stellar envelope and produce the gamma-ray emission we observe. It's a violent, chaotic process involving some of the most extreme conditions in the universe, and it releases more energy in a few seconds than the Sun will produce in its entire 10 billion-year lifetime. But as extreme as collapsars are, they're not the only game in town. Short gamma-ray bursts, those mysterious flashes lasting less than 2 seconds, arise from a completely different mechanism: the merger of two neutron stars. And, in some ways, neutron star mergers are even more extreme than collapsers. To understand neutron star mergers, we first need to appreciate just how strange neutron stars are. A neutron star is the collapsed core of a massive star, left behind after a supernova explosion. Unlike the progenitors of gamma-ray bursts, which collapse all the way to black holes, the stars that produce neutron stars are massive enough to explode, but not massive enough for their cores to keep collapsing beyond the neutron star stage. The result is an object that packs roughly 1.5 times the mass of the Sun into a sphere about 20 kilometers across, roughly the size of a medium city. To put that in perspective, a teaspoon of neutron star material would weigh about 6 billion tons, roughly equal to the entire human population multiplied by 1,000,000. The density is so extreme that the electrons and protons that normally make up matter are crushed together to form neutrons, hence the name. The entire star is essentially one giant atomic nucleus, held together by gravity and supported against further collapse by the quantum mechanical pressure of neutrons refusing to be squeezed any closer together. Neutron stars are also intensely magnetic, with magnetic fields typically 1 trillion times stronger than Earth's. They rotate rapidly, some spinning hundreds of times per second, and they're incredibly hot when first formed, with surface temperatures of millions of degrees. Many neutron stars are observed as pulsars, appearing to flash on and off as their beams of radio emission sweep across our line of sight like a cosmic lighthouse. The regularity of pulsar signals is so precise that they can be used as natural clocks, and it was observations of a pulsar in a binary system that provided the first indirect evidence for gravitational waves, decades before LIGO made its first direct detection. This brings us to the heart of the neutron star merger scenario. Neutron stars don't form in isolation. Many of them are born in binary systems, pairs of massive stars orbiting each other. When both stars eventually explode as supernovae, they can leave behind a binary neutron star system. Two incredibly dense, rapidly rotating objects locked in a gravitational embrace, orbiting their common center of mass. Here's where Einstein's general relativity comes into play. According to Einstein's theory, any accelerating mass produces ripples in the fabric of spacetime itself, disturbances that propagate outward at the speed of light. These are gravitational waves, and while they're produced by any accelerating mass, they're only significant for the most extreme systems. Two neutron stars orbiting each other are constantly accelerating, constantly changing direction as they swing around their mutual center of gravity, and this means they're constantly producing gravitational waves. The energy carried away by these waves has to come from somewhere, and that somewhere is the orbital energy of the binary system. As the neutron stars radiate gravitational waves, they gradually lose energy, which causes them to spiral closer together. The closer they get, the faster they orbit, and the more gravitational waves they emit, which causes them to spiral even closer. It's a runaway process, but an incredibly slow one by human standards. The first binary pulsar discovered, PSR B1913 plus E16, has been observed since 1974. Over that time, astronomers have watched its orbit shrink at exactly the rate predicted by general relativity, providing stunning confirmation of Einstein's theory. But even at this rate, the two neutron stars in that system won't merge for another 300 million years. Other binary neutron star systems are further along in this process. Some are already close enough that they'll merge within millions of years. cosmic timescales that are short by astronomical standards, but still far beyond any human planning horizon. When a neutron-star merger finally occurs, it happens fast. In the final seconds before collision, the two objects are orbiting each other hundreds of times per second, producing gravitational waves that sweep upward in frequency like a cosmic chirp. This is the signal that LIGO and Virgo detected on August 17, 2017, when they observed GWS 7817. The gravitational wave signal was audible for about 100 seconds as the neutron stars completed their final dance, but the actual merger itself took only a fraction of a second. When the two neutron stars finally touch, they don't simply bounce off each other. They're traveling too fast and their gravity is too strong for that. Instead, they smash together in a catastrophic collision that releases an enormous amount of energy. The violence of the impact strips material off both stars, sending sprays of neutron-rich matter outward at a significant fraction of the speed of light. What happens next depends on the total mass of the system. If the combined mass is below a certain threshold, the merger might produce a single, rapidly spinning neutron star, at least temporarily. This hypermassive neutron star would be rotating so fast that centrifugal force helps support it against collapse, but it can't last. Within milliseconds to seconds, the star loses angular momentum and collapses into a black hole. If the combined mass is above the threshold, the collapse to a black hole is essentially instantaneous. Either way, the end result is a black hole surrounded by an accretion disk of hot, dense material, the debris from the destroyed neutron stars. And, just like in the collapsor model, this accretion disk launches relativistic jets that produce a gamma-ray burst. The key difference is timescale. In a collapsar, the central engine operates for seconds to minutes, producing a long gamma-ray burst. In a neutron-star merger, the entire process, from first contact to jet launch, takes less than a second, producing a short gamma-ray burst. The shorter duration reflects the smaller amount of material involved and the more compact geometry of the system. The detection of GWS 70817 and GRB 170817A confirmed this basic picture in spectacular fashion. The gravitational wave signal told us that two neutron stars had merged, and the gamma-ray burst told us what happens when they do. But there was one surprise. The gamma-ray burst was much fainter than expected. GRB 1707A was between 100 and 1,000,000 times less energetic than typical short bursts observed at similar distances. This wasn't because the merger was unusually weak, but because we weren't looking straight down the jet. Analysis of the afterglow emission revealed that we were viewing the burst from an angle of about 30 degrees off-axis, seeing only the edge of the emission cone rather than the full blast. This was actually fortunate for the purposes of understanding the physics. An on-axis burst would have been so bright that it would have overwhelmed our instruments, making detailed observations difficult. The off-axis viewing angle allowed astronomers to study the structure of the jet and the properties of the surrounding cocoon of material with unprecedented detail. But the gamma-ray burst was only part of the story. Perhaps even more exciting was the kilonova, the optical and infrared emission powered by the radioactive decay of heavy elements synthesized in the merger. When neutron stars collide, the extreme conditions, enormous densities, high temperatures, intense neutron fluxes provide the perfect environment for a process called rapid neutron capture, or the R process. In the R process, atomic nuclei are bombarded with neutrons faster than they can decay, building up heavier and heavier elements in a matter of seconds. This is thought to be the origin of about half the elements heavier than iron in the periodic table, including gold, platinum, and uranium. The neutron star merger observed in 2017 is estimated to have produced several Earth masses worth of gold and platinum, flung out into space at a significant fraction of light speed. This material, initially composed of highly unstable neutron-rich nuclei, undergoes rapid radioactive decay, producing the heat that powers the kilonova emission. Observations of the kilonova associated with GW 170817 confirmed the presence of R process elements, including specific signatures of tellurium and other heavy metals. So neutron star mergers aren't just sources of gamma-ray bursts, they're cosmic foundries, manufacturing the heavy elements that eventually end up in planets and people. The gold in your wedding ring, the platinum in your catalytic converter, the uranium that powers nuclear reactors. All of it was probably forged in the collision of neutron stars billions of years ago, scattered into space and eventually incorporated into the cloud of gas and dust that collapsed to form our solar system. In a very real sense, neutron star mergers are part of our origin story. They're also, as we'll see, potential threats to our continued existence. Because while the merger that produced GW 170817 occurred 130 million light-years away, neutron star binaries exist within our own galaxy as well. The Hulse-Taylor binary pulsar will merge in about 300 million years. Other binaries, yet undiscovered, may be much closer to collision. Now, there's one more aspect of gamma-ray burst physics that we need to discuss before moving on, and that's the question of how much energy we're actually dealing with. I've thrown around phrases like, more energy than the sun produces in its lifetime a few times now, but that's such an astronomical number that it's hard to really grasp what it means. Let's try to put it in perspective. The sun's luminosity, the rate at which it's radiating energy, is about 3.8 times 10 to the 26 watts. That's 380 yottawatts, or 380 trillion watts. Every second, the sun is pumping out enough energy to power human civilization for about 500,000 years at current consumption rates. Over its 10 billion-year lifetime, the sun will produce a total of about 1.2 times 10 to the 44 joules of energy. This is an almost unimaginably large number, but we can at least get a sense of its scale. Now consider that a typical long gamma-ray burst releases about 10 to the 44 joules of energy in its jets alone. That's roughly equal to the sun's entire lifetime energy output, released in a matter of seconds. The power output during the burst can exceed 10 to the 45 watts, about 1 trillion times the luminosity of an entire galaxy containing hundreds of billions of stars. For those brief seconds, a single dying star outshines everything else in the observable universe combined. Of course, this energy isn't radiated uniformly in all directions. The beaming effect concentrates the emission into two narrow cones, each perhaps 10 degrees in diameter. This means that the total energy is about 100 times less than it would be for isotropic emission. But even accounting for beaming, gamma-ray bursts release something like 10 to the 42 to 10 to the 44 joules of energy, depending on the specific burst. For comparison, the most powerful nuclear weapon ever detonated, the Soviet Tsar Bomba, released about 2 times 10 to the 17 joules of energy. A gamma-ray burst releases roughly 100 trillion times more energy than the largest nuclear weapon. The asteroid impact that killed the dinosaurs released about 4 times 10 to the 23 joules. A gamma-ray burst is about 100 billion times more energetic than the Chicxulub impact. We're not talking about explosions that are a little bigger than familiar catastrophes. We're talking about events that are incomparably mind-bogglingly more powerful than anything in human experience. Short gamma-ray bursts from neutron star mergers are somewhat less energetic than long bursts, typically releasing 10 to the 42 to 10 to the 43 joules. But they make up for it in other ways. Because neutron star mergers produce not just gamma rays but also gravitational waves and colonovae, the total energy budget of a merger event is actually comparable to or even greater than a collapsar. The gravitational wave energy alone from GW-BOTS 70817 was estimated at about 3% of the combined mass of the two neutron stars converted into pure gravitational radiation, something like 10 to the 46 joules. Most of this energy passed through Earth without any noticeable effect. Gravitational waves interact very weakly with matter, which is why they're so hard to detect. But the gamma rays and kilonova emission are different. They interact strongly with matter, and that's what makes them dangerous. The numbers we've been throwing around might seem so large as to be meaningless, but they have very real implications for what would happen if a gamma-ray burst occurred close to Earth. The inverse square law tells us that the intensity of radiation falls off with the square of the distance from the source. A burst that's twice as far away appears 4 times dimmer. A burst that's 10 times closer appears 100 times brighter. The bursts we observe from cosmological distances are incredibly faint compared to how they appear at their source. GRB 170817A, for example, was 130 million light-years away. If it had occurred at a distance of 130 light-years instead, a million times closer, the gamma-ray fluence at Earth would have been 1 trillion times higher. Instead of being an interesting astronomical observation, it would have been a global catastrophe. This is not an exaggeration. The energy involved in gamma-ray bursts is so extreme that even at distances of thousands of light-years, a direct hit could have devastating effects on our planet's atmosphere and biosphere. We'll explore exactly how this works in the next section, but the basic point is simple. Gamma-ray bursts are not just distant curiosities. They're potential extinction-level threats, and understanding their physics is the first step toward understanding the danger they pose. Before we move on to the effects of gamma-ray bursts on Earth, there's one more recent development worth mentioning. On October 9, 2022, Earth was struck by the brightest gamma-ray burst ever recorded. Designated GRB 22/1009A, this event was so intense that it earned the nickname the Boat, the brightest of all time. The burst originated from a galaxy about 1.9 billion light-years away, relatively close by cosmic standards, and it lasted for about 800 seconds, classifying it as a long gamma-ray burst from a collapsing massive star. What made GRB 22/1009A exceptional was its sheer brightness. It was roughly 70 times more luminous than the previous record holder, saturating the detectors on multiple gamma-ray satellites. The Fermi Gamma-Ray Space Telescope, which has observed thousands of bursts over its operational lifetime, had never seen anything like it. Statistical analysis suggests that a burst this bright occurs perhaps once every 10,000 years, making it a truly rare event to witness in a human lifetime. But the Boat wasn't just a record-breaking light show. It also provided a sobering demonstration of how gamma-ray bursts can affect Earth even from cosmological distances. Despite being nearly 2 billion light-years away, GRB 22/1009A was powerful enough to measurably ionize Earth's atmosphere. The burst's gamma rays penetrated deep into the upper atmosphere, stripping electrons from atoms and molecules and creating a pulse of ionization that disturbed the ionosphere for several hours. Very low-frequency radio signals, which propagate by bouncing between the ground and the ionosphere, showed clear signatures of the disturbance. Lightning detectors in India and Germany registered the impact. The burst had physically touched our planet from across nearly a tenth of the observable universe. Now, the effects of GRB 22109A on Earth were minor, interesting to scientists, but completely harmless to life. The ionospheric disturbance was comparable to what a small to medium solar flare might produce, nothing that poses any danger. But the detection served as a powerful reminder of the principle at stake. If a burst that bright could affect Earth from 2 billion light-years away, what would happen if a much closer burst, even one less intrinsically luminous, occurred within our own galaxy? The boat also prompted renewed interest in studying the aftereffects of gamma-ray bursts on planetary atmospheres. Scientists have long modeled what a nearby burst would do to Earth's ozone layer, but GRB 22109A provided actual data on how gamma rays interact with the upper atmosphere in real time. This data will help refine our models and improve our understanding of the threat that gamma-ray bursts pose to inhabited planets. It's also worth noting what we learned from the boat about the physics of the burst itself. Follow-up observations with the James Webb Space Telescope confirmed that the burst was produced by a collapsar, the collapse of a massive star into a black hole. The supernova associated with the burst was detected, though it was surprisingly faint given how bright the gamma-ray emission had been. Even more intriguingly, the expected signatures of heavy element production, the R process elements that should have been forged in the explosion, were not detected. This was unexpected, since collapsars were thought to be one of the primary sites for R process nucleosynthesis, alongside neutron star mergers. The absence of R process signatures in the boat's aftermath suggests that our understanding of heavy element production is still incomplete, and that the relative contributions of collapsars and neutron star mergers to the cosmic abundance of elements like gold and uranium may need to be revised. These ongoing mysteries remind us that while we've learned an enormous amount about gamma-ray bursts since their accidental discovery in 1967, there's still much we don't understand. The basic mechanisms, collapsars, and neutron star mergers seem well established, but the details of jet launching, energy extraction, and element synthesis remain active areas of research. New observations continue to surprise us, revealing bursts that don't fit neatly into our existing categories or that challenge our theoretical models. This is how science works. We build the best models we can based on available data, then refine and revise them as new data comes in. But for the purposes of understanding the threat that gamma-ray bursts pose to Earth, we know enough. We know that these events release enormous amounts of energy, concentrated into narrow beams moving at nearly the speed of light. We know that they occur throughout the universe, including in galaxies like our own. We know that a burst aimed at Earth from within the Milky Way could deliver enough radiation to significantly damage our planet's protective ozone layer. And we know that such events have probably happened multiple times over the 4.5 billion years of Earth's history. What we don't know is exactly when the next one will occur, or whether it will be pointed in our direction. That uncertainty is perhaps the most unsettling aspect of the gamma-ray burst threat. Unlike asteroid impacts, which we can potentially detect and deflect with enough warning, or supernovae, which we can predict based on the properties of nearby stars, gamma-ray bursts provide no advance warning whatsoever. The first sign of a burst aimed at Earth would be the burst itself, arriving at the speed of light with no possibility of evasion or defense. We would have no time to prepare, No time to take shelter, no time to do anything at all. The gamma rays would simply arrive, and whatever effects they were going to have would begin immediately. The question of what those effects would be, and whether they've shaped the history of life on our planet, is what we'll turn to next. But before we do, let's take a moment to appreciate the strange position we find ourselves in. We've discovered a phenomenon of almost unimaginable violence, explosions that dwarf anything else in the universe, that could potentially threaten life on Earth, and we found it entirely by accident while looking for Soviet nuclear tests. The cosmos, it seems, has a dark sense of humor. So we've established that gamma-ray bursts are the most powerful explosions in the universe, releasing more energy in seconds than the Sun will produce in its entire lifetime. We've explored the physics of collapsers and neutron star mergers, the two mechanisms responsible for these cosmic cataclysms. Now comes the uncomfortable part. What would actually happen if one of these events occurred close enough to Earth for us to feel it? Not just detect it with our instruments, but actually feel it in the air we breathe, the water we drink, the sunlight that reaches our skin. The answer involves a chain of events that starts in the upper atmosphere and cascades down through every level of Earth's biosphere. It's a story of invisible chemistry, deadly radiation, and the fragile shield that stands between us and the hostile universe beyond. Let's start with what gamma rays actually are. Gamma rays are photons, particles of light, just like the visible light that lets you read, these words, or the radio waves that carry your favorite music. The only difference is energy. Visible light photons have energies of a few electron volts. Radio waves have even less. But gamma rays are at the extreme high end of the electromagnetic spectrum, with energies ranging from thousands to billions of electron volts. This enormous energy is what makes gamma rays so dangerous. When a gamma ray photon strikes an atom, it doesn't just bounce off or pass through harmlessly. It has enough energy to knock electrons out of their orbits, ionizing the atom and potentially breaking molecular bonds. In living tissue, this ionizing radiation can damage DNA, kill cells, and cause cancer. A large enough dose can cause radiation sickness and death within days or hours. Fortunately for us, Earth has a built-in defense against gamma rays from space, our atmosphere. The blanket of air above our heads is remarkably effective at absorbing high-energy radiation. Gamma rays from a distant burst don't penetrate to the surface. Instead, they're absorbed high in the atmosphere, dozens of kilometers above our heads. If that were the end of the story, gamma-ray bursts would be nothing more than an interesting astronomical phenomenon with no relevance to life on Earth. But absorption isn't the same as harmless disappearance. When gamma rays are absorbed by the atmosphere, they deposit their energy into the air molecules they strike, and that energy has to go somewhere. What happens is a cascade of chemical reactions that transforms the composition of the upper atmosphere in ways that have profound consequences for life on the surface below. The key players in this drama are nitrogen and oxygen, the two gases that make up about 99% of Earth's atmosphere. Under normal conditions, these gases exist primarily as molecular nitrogen and molecular oxygen, two atoms bonded together. But when gamma rays slam into these molecules, they have enough energy to break those bonds, splitting the molecules into individual nitrogen and oxygen atoms. These highly reactive atoms then recombine in new ways, forming compounds that wouldn't normally exist in significant quantities. The most important of these compounds are the nitrogen oxides, nitric oxide and nitrogen dioxide. These molecules are produced when nitrogen and oxygen atoms combine in the aftermath of gamma-ray absorption. Under normal circumstances, nitrogen oxides are present in the atmosphere only in trace amounts, produced by lightning, volcanic eruptions, and human industrial activity. But a nearby gamma-ray burst could produce enormous quantities of nitrogen oxides in a matter of seconds, fundamentally altering the chemistry of the upper atmosphere. Why does this matter? Because nitrogen oxides are extraordinarily effective at destroying ozone. Ozone is a molecule consisting of 3 oxygen atoms bonded together, and it exists primarily in a layer of the stratosphere between about 15 and 35 kilometers above the surface. This ozone layer is critically important for life on Earth because it absorbs ultraviolet radiation from the sun. Without the ozone layer, the full intensity of solar UV would reach the surface, causing widespread damage to living organisms. Ultraviolet radiation is divided into 3 categories based on wavelength. UVA, with wavelengths between 315 and 400 nanometers, is relatively benign and is responsible for tanning. UVB, with wavelengths between 280 and 315 nanometers, is more energetic and causes sunburn, DNA damage, and skin cancer. UVC, with wavelengths below 280 nanometers, is the most dangerous, but is almost completely absorbed by the atmosphere before reaching the surface. The ozone layer is particularly effective at blocking UVB and UVC radiation, and it's this shielding effect that makes complex life on land possible. The problem is that ozone is constantly being created and destroyed in the stratosphere through natural processes. Ultraviolet light from the sun breaks apart oxygen molecules, and the resulting oxygen atoms combine with other oxygen molecules to form ozone. But ozone is also destroyed by reactions with various chemicals, including nitrogen oxides. Under normal conditions, these creation and destruction processes are roughly in balance, maintaining a more or less constant concentration of ozone in the stratosphere. But a massive injection of nitrogen oxides from a gamma-ray burst would tip this balance dramatically toward destruction. The chemistry is insidious. Nitrogen oxide molecules don't just destroy one ozone molecule and then disappear. Instead, they act as catalysts, participating in a cycle of reactions that destroys ozone while regenerating the nitrogen oxide to destroy more ozone. A single nitrogen oxide molecule can destroy thousands of ozone molecules before it's eventually removed from the stratosphere through other processes. This catalytic destruction is why even relatively small amounts of nitrogen oxides can have such a large impact on the ozone layer. Scientists have modeled what would happen to Earth's ozone layer in the event of a nearby gamma-ray burst. The results are sobering. A burst within a few thousand light-years, delivering effluence of about 100 kilojoules per square meter at Earth's surface, could deplete the global ozone layer by 35 to 40% on average. But this average hides significant regional variation. The depletion would be most severe in the hemisphere facing the burst and at high latitudes, where atmospheric circulation patterns concentrate the nitrogen oxides. In some regions, ozone depletion could reach 70 to 75%. To put this in perspective, the Antarctic ozone hole that caused so much concern in the 1980s and 1990s involved ozone depletion of about 50 to 60% over a relatively small area of the planet. A gamma-ray burst could produce comparable or worse depletion across an entire hemisphere. The consequences of such severe ozone depletion would be catastrophic for life on Earth. With the ozone shield compromised, ultraviolet radiation at the surface would increase dramatically. Models suggest that DNA damage rates could increase by up to 16 times the normal level, well above the threshold that most organisms can tolerate. Humans would experience severe sunburns within minutes of exposure, and skin cancer rates would skyrocket. But the effects on human health, while serious, would be dwarfed by the impact on the broader biosphere. Plants, which can't seek shelter from the sun, would suffer widespread damage to their leaves and photosynthetic systems. Phytoplankton, the microscopic marine organisms that form the base of the ocean food chain, would be particularly vulnerable. These tiny creatures live near the ocean surface, where they're exposed to the full intensity of incoming sunlight. An increase in UV radiation would devastate phytoplankton populations, with cascading effects throughout the marine ecosystem. Phytoplankton are also responsible for producing a significant fraction of the oxygen we breathe, so their decline would have implications far beyond the oceans. Perhaps most troubling is how long these effects would last. Unlike the prompt gamma-ray emission, which lasts only seconds to minutes, the ozone depletion would persist for years. The nitrogen oxides produced by the burst don't simply disappear once the gamma rays stop. They remain in the stratosphere, continuing to catalyze ozone destruction until they're gradually removed by chemical reactions and transport to lower altitudes. Models suggest that significant ozone depletion, at least 10% below normal levels, would persist for roughly 7 years after a major burst. During this entire period, life on Earth would be exposed to elevated UV radiation, with all the consequences that entails. Recovery of the ozone layer would be slow, with full recovery potentially taking a decade or more depending on the severity of the initial depletion. But ozone destruction isn't the only atmospheric effect of a gamma-ray burst. The nitrogen dioxide produced by the burst is a brownish gas that absorbs visible light. In sufficient quantities, it can create a photochemical smog that darkens the sky and reduces the amount of sunlight reaching the surface. Models suggest that this dimming effect would be relatively modest, perhaps a few percent reduction in visible light, but it could still have significant consequences. Reduced sunlight means reduced photosynthesis, which means reduced plant growth and reduced food production. The effect would be most pronounced at high latitudes, where the sun is already low in the sky for much of the year. For ecosystems already operating near the edge of viability, even a small reduction in available sunlight could push them over the brink. There's also the possibility of global cooling. The same nitrogen dioxide that dims the sky would also affect Earth's energy balance, potentially triggering a period of reduced temperatures. The magnitude of this effect is uncertain and depends on various factors, including the total amount of nitrogen dioxide produced and how long it remains in the atmosphere. Some models suggest that a nearby gamma-ray burst could trigger rapid cooling, potentially even initiating an ice age if conditions were right. This cooling would compound the stress on ecosystems already struggling with increased UV radiation and reduced photosynthesis. Finally, the nitrogen oxides would eventually be converted to nitric acid and rain out of the atmosphere. This acid rain would add another stress to terrestrial and aquatic ecosystems, though models suggest the effect would be relatively modest compared to the UV and cooling impacts. In some scenarios, the increased nitrogen deposition might actually benefit certain plants, providing a fertilizing effect that partially offsets other damage. But this silver lining would be small consolation for a biosphere reeling from multiple simultaneous assaults. The picture that emerges from these models is of a cascading catastrophe that would unfold over years, following a nearby gamma-ray burst. The immediate effect, the absorption of gamma rays in the upper atmosphere, would be invisible and imperceptible to anyone on the surface. But within days, the chemical consequences would begin to manifest. Ozone levels would plummet. UV radiation at the surface would spike. Plants and animals would start to show signs of radiation damage. Phytoplankton populations would crash, sending shock waves through marine food webs. The sky might take on a brownish tinge as nitrogen dioxide accumulated, and temperatures might begin to drop. Over months and years, these effects would compound, potentially triggering a mass extinction event comparable to the great die-offs recorded in the geological record. And here's the really unsettling part. There would be no warning. Gamma rays travel at the speed of light, so the first indication of a burst would be the burst itself. There would be no chance to prepare, no opportunity to seek shelter, no time to evacuate vulnerable populations. The gamma rays would arrive, the atmospheric chemistry would change, and the cascade of consequences would begin, all before anyone knew what was happening. By the time scientists figured out what had occurred, the damage would already be done. All we could do is watch the ozone layer thin, monitor the rising UV levels, and wait for the slow process of recovery to begin. The question that inevitably arises once you understand what gamma-ray bursts can do to a planet is whether one has ever actually hit Earth. We've been talking in hypotheticals, describing what would happen if a burst occurred nearby. But Earth has been orbiting the Sun for 4.5 billion years, and gamma-ray bursts have been occurring throughout the universe for even longer. Over such vast stretches of time, the probability that at least one burst has struck our planet starts to look uncomfortably high. And if it has happened, we might expect to find evidence of it somewhere in the geological record, perhaps associated with one of the mass extinction events that have periodically devastated life on Earth. This brings us to the late Ordovician mass extinction, the second most severe die-off in the history of complex life, and a tantalizing hypothesis that has captured the imagination of scientists and the public alike. About 450 million years ago, during a period known as the Ordovician, Earth was a very different place. The continents were arranged in unfamiliar configurations, with most landmass concentrated in the southern hemisphere. Life had not yet colonized the land in any significant way. There were no trees, no insects, no vertebrates walking on 4 legs. But the oceans teemed with diversity. Trilobites, those iconic arthropods with their segmented bodies and compound eyes, had radiated into thousands of species occupying every ecological niche. Brachiopods, creatures resembling clams but unrelated to them, carpeted the seafloor. Corals were building the first great reef systems. Nautiloid cephalopods, ancestors of today's squids and octopuses, hunted through the water column. Graptolites, colonial organisms that floated near the surface, were so abundant that their fossils would later give their name to entire geological formations. The Ordovician was, by some measures, the most biodiverse period in Earth's history up to that point. The culmination of what paleontologists call the Great Ordovician Biodiversification Event. And then, over a geologically brief period at the end of the Ordovician, roughly 85% of all marine species went extinct. The late Ordovician mass extinction, as it's now known, wiped out entire families of trilobites, brachiopods, and bryozoans. Coral reefs collapsed. Graptolite diversity plummeted. The extinction occurred in 2 distinct pulses, separated by perhaps 1 million years, each one devastating in its own right. Together, They rank as the second worst mass extinction in Earth's history, exceeded only by the catastrophic Permian extinction 200 million years later. For decades, the cause of the late Ordovician extinction was attributed primarily to climate change. Geological evidence shows that the period immediately preceding the extinction was relatively warm, but then temperatures dropped rapidly, and ice sheets formed over the southern supercontinent of Gondwana. Sea levels fell as water was locked up in glaciers, destroying the shallow marine habitats where most Ordovician life resided. Then, as the glaciation ended and temperatures rose again, the second pulse of extinction struck. The traditional explanation holds that organisms couldn't adapt quickly enough to these rapid environmental changes. First, the cooling and sea level drop, then the warming and sea level rise. But in 2003, a team of scientists led by Adrian Mellott of the University of Kansas proposed a different hypothesis. What if the glaciation itself was triggered by something external? What if a gamma ray burst, occurring somewhere in the nearby galaxy, had struck Earth with enough force to devastate the ozone layer and alter the climate? The gamma ray burst hypothesis, as it came to be known, was published in the International Journal of Astrobiology, and immediately attracted attention both for its boldness and for its implications. If correct, it would mean that events occurring light years away could influence the course of evolution on Earth, that the history of life is shaped not just by terrestrial processes, but by the cosmic environment in which our planet is embedded. The evidence supporting the hypothesis is circumstantial but intriguing. First, there are the patterns of extinction and survival themselves. In most mass extinctions, species with wide geographic ranges tend to survive better than those with restricted distributions. Being spread across multiple regions provides insurance. Even if conditions become lethal in one area, populations elsewhere might pull through. But in the late Ordovician extinction, this pattern was reversed for some groups. Trilobites that lived near the ocean surface, including species with larvae that spent time in the plankton layer, were hit much harder than their deep-water relatives. Surface-dwelling brachiopods fared worse than those that burrowed into the sediment. Graptolites, which floated near the surface, were devastated. This pattern is exactly what you would expect if increased ultraviolet radiation were a major killing mechanism. UV light penetrates only the upper layers of the ocean. Organisms living near the surface would be exposed to the full intensity, while those in deeper water would be protected. The traditional climate explanation doesn't easily account for this depth-dependent pattern of extinction. Second, there's the timing and rapidity of the glaciation. The onset of ice ages is typically a gradual process, driven by slow changes in atmospheric composition, continental positions, or orbital parameters. But the late Ordovician glaciation appears to have begun quite abruptly, catching a warm-adapted biosphere off guard. A gamma-ray burst could potentially trigger rapid cooling through the atmospheric effects we discussed earlier. The nitrogen dioxide produced by the burst would darken the sky, reducing the amount of solar energy reaching the surface. More importantly, the destruction of the ozone layer could alter atmospheric chemistry in ways that affect the global energy balance. Some models suggest that these effects, combined with the right initial conditions, could push a warm climate over a tipping point into a glacial state. Third, there's the fact that gamma-ray bursts within the danger zone are not implausibly rare. Estimates vary, but most calculations suggest that a burst capable of causing significant ozone depletion should occur within a few thousand light-years of Earth roughly once every few 100 million years. Over the 450 million years since the Ordovician, we would expect one or two such events to have occurred. The probability isn't high enough to make gamma-ray bursts a likely explanation for any given extinction, but it's high enough that we can't rule them out either. And, of all the major extinctions in Earth's history, the late Ordovician has characteristics that fit the gamma-ray burst scenario better than most. Of course, the hypothesis has its critics, and their objections are worth taking seriously. The most fundamental problem is the lack of direct physical evidence. Unlike asteroid impacts, which leave behind telltale signatures like iridium layers and shocked quartz, gamma-ray bursts don't deposit any distinctive material on Earth's surface. There's no smoking gun, no unambiguous marker that would prove a burst occurred at a particular time. The patterns of extinction that support the hypothesis could potentially be explained by other mechanisms. Perhaps the depth-dependent survival of trilobites and brachiopods reflects something about their life histories or ecological requirements that we don't fully understand. Perhaps the rapid onset of glaciation was triggered by volcanic activity or changes in ocean circulation rather than extraterrestrial radiation. The late Ordovician extinction remains an active area of research, and the gamma-ray burst hypothesis, while still taken seriously by many scientists, has not achieved consensus acceptance. There have been attempts to find more direct evidence. Some researchers have looked for isotopic anomalies in rocks from the extinction boundary, signatures that might indicate exposure to intense radiation. Others have searched for evidence of increased cosmic ray flux in the form of certain radioactive isotopes that would be produced by high-energy particles striking the atmosphere. So far, these searches have not yielded definitive results. The problem is that any signal from a gamma-ray burst 450 million years ago would be subtle at best, potentially erased or obscured by the many geological processes that have affected those ancient rocks since then. The absence of evidence isn't necessarily evidence of absence. It might simply mean that the evidence is too faint to detect with current techniques. What makes the gamma-ray burst hypothesis compelling despite the lack of direct proof is its explanatory power. It provides a mechanism that could plausibly produce the observed pattern of extinction, the rapid climate change, and the differential survival of surface versus deep water organisms, all from a single cause. It connects events on Earth to the broader cosmic environment in a way that feels both sobering and scientifically satisfying. And it reminds us that our planet doesn't exist in isolation, that we're part of a universe filled with violent phenomena that could, under the right circumstances, reach across light years to affect life here. Whether or not a gamma-ray burst actually caused the late Ordovician extinction, the hypothesis has had a valuable effect on how scientists think about mass extinctions and cosmic threats. It has prompted new research into the atmospheric effects of high-energy radiation, the patterns of extinction and survival in past die-offs, and the frequency and distribution of gamma-ray bursts in the galaxy. It has raised awareness of the fact that space, while mostly empty and benign, contains hazards that we ignore at our peril. And it has led to a broader recognition that the history of life on Earth is intertwined with the history of the cosmos in ways we're only beginning to understand. The implications extend beyond the Ordovician. If gamma-ray bursts have struck Earth in the past, they will presumably strike again in the future. The universe doesn't care about our survival. It simply goes on producing supernovae, collapsers, and neutron star mergers according to the laws of physics, indifferent to whether any of them happen to be pointed at inhabited planets. We've been lucky so far, or at least lucky enough that our species has survived to ask these questions. But luck, by definition, doesn't last forever. The same cosmic lottery that has spared us so far could turn against us at any moment, with no warning and no possibility of defense. This may sound fatalistic, but it's simply realistic. Understanding the threats we face, even threats we can do nothing about, is valuable in itself. It puts our existence in perspective, reminding us how contingent and fragile life on Earth really is. It motivates us to learn more about the universe we inhabit, to improve our ability to detect and characterize gamma-ray bursts, and to understand their effects on planetary atmospheres and biospheres. And it underscores the importance of becoming a multiplanetary species, of spreading life beyond Earth so that no single cosmic catastrophe can wipe us out entirely. These are long-term goals, to be sure, but they're grounded in the recognition that Earth, for all its beauty and abundance, is not a permanent safe haven. The universe is vast and ancient and violent, and we're very, very small. So we've established that gamma-ray bursts are real, that they're incredibly powerful, that they could devastate Earth's biosphere if one occurred nearby, and that one may have already contributed to a mass extinction 450 million years ago. The natural question at this point is, should we be worried? Is there a gamma-ray burst out there with our name on it, a cosmic gun pointed at Earth just waiting to go off? The answer, thankfully, is probably not. But probably is doing a lot of heavy lifting in that sentence, and the reasons behind our relative safety are worth exploring in detail. Because while the odds of a gamma-ray burst striking Earth in any given year are vanishingly small, the consequences would be so severe that even a tiny probability deserves serious consideration. Let's start with the most famous candidate for a nearby gamma-ray burst progenitor, a Wolf-Rayet star system called WR-104, located in the constellation Sagittarius. WR-104 first attracted attention in the late 1990s when astronomers using the Keck telescope in Hawaii captured stunning images of a spiral pattern of dust surrounding the system. This pinwheel nebula, as it came to be called, is created by the interaction of stellar winds from two massive stars orbiting each other. As the stars swing around their common center of mass, their winds collide and compress, allowing dust to form in the cooler regions where the winds meet. The rotation of the binary system sweeps this dust into a beautiful spiral pattern that expands outward into space. The images were scientifically valuable for what they revealed about stellar wind interactions, but they also raised a troubling question. The pinwheel appeared to be oriented almost perfectly face-on to Earth, which meant we were looking straight down the rotation axis of the system. And if a gamma-ray burst were to occur in WR-104, its jets would be launched along that same axis, potentially aimed directly at our planet. The media coverage was predictably sensational. Headlines proclaimed that a Death Star was aimed at Earth, that we could be sterilized at any moment by a cosmic ray gun. Astronomers who had published the original research found themselves fielding calls from worried members of the public and irritated colleagues who felt the threat had been overblown. The reality, as is often the case, was considerably more nuanced than the headline suggested. Yes, WR-104 contains a Wolf-Rayet star that will eventually explode as a supernova, possibly within the next few 100,000 years. And yes, some supernovae of this type produce gamma-ray bursts, but the probability that WR-104 will produce a burst, and that any such burst would be dangerous to Earth, turns out to be quite low when you examine the details. The first issue is distance. WR-104 is located somewhere between 2,000 and 8,000 light-years from Earth, with most estimates placing it around 2,500 light-years away. This is close by galactic standards, but not point-blank range. At this distance, a gamma-ray burst would need to be both powerful and well-aimed to pose a serious threat. The danger zone for significant ozone depletion is thought to extend only a few thousand light-years at most, so WR-104 is right on the edge of being concerning. A burst at the closer end of the distance estimates would be more worrisome than one at the farther end. The second issue is orientation. While the initial images suggested we were looking straight down the rotation axis of the system, more recent observations have revised this picture significantly. Spectroscopic studies conducted at the Keck Observatory in 2009 and published more recently in 2024 and 2025 indicate that the system's orbital plane is actually tilted by 30 to 40 degrees relative to our line of sight. This is a crucial finding because it means any jets produced by a supernova or gamma-ray burst would be aimed well away from Earth. The opening angle of a typical gamma-ray burst jet is thought to be around 10 to 20 degrees, so a misalignment of 30 degrees or more would place us safely outside the danger zone. The jets would sail off harmlessly into space in a different direction, and we would see only a distant supernova, bright but not dangerous. The third issue is whether WR-104 will produce a gamma-ray burst at all. Not every collapsing massive star generates the relativistic jets that characterize gamma-ray bursts. In fact, the conditions required for jet formation appear to be quite specific. The progenitor star must be rotating rapidly, and it must have lost its outer hydrogen envelope to allow the jets to punch through to the surface. Wolf-Rayet stars meet the second criterion by definition, since they've shed their outer layers through powerful stellar winds. But the rotation requirement is more problematic. Stars in our galaxy, including WR-104, tended to be relatively metal-rich, meaning they contain significant amounts of elements heavier than hydrogen and helium. These heavy elements increase the opacity of the stellar material, which enhances the coupling between the star's radiation field and its outer layers. This coupling tends to slow the star's rotation over time as angular momentum is carried away by the stellar wind. In metal-poor galaxies, where this braking mechanism is less effective, stars can maintain rapid rotation until they die, creating the conditions for gamma-ray bursts. But in the metal-rich environment of the Milky Way, stars may spin down too much to produce bursts. This metallicity effect is supported by observations. Gamma-ray bursts are observed preferentially in small metal-poor galaxies, not in large spiral galaxies like our own. No gamma-ray burst has ever been confirmed to have originated within the Milky Way, though our galaxy certainly contains stars massive enough to produce them in principle. This suggests that conditions in the Milky Way are not particularly conducive to gamma-ray burst formation. Peter Totehill, the astronomer who led the original observations of WR-104, has estimated the probability that the star will produce any kind of gamma-ray burst at around 1%, and he cautions that more research is needed even to have confidence in that figure. When you combine all these factors, the threat from WR-104 starts to look much less alarming. The star is probably too far away to cause severe damage. The system is probably tilted enough that any jets would miss us. And the star probably won't produce a gamma-ray burst anyway. That's a lot of probablys, and in science we prefer certainty, but the cumulative effect is to reduce the risk from WR-104 to something that most astronomers consider negligible. You're far more likely to be killed by a lightning strike, a car accident, or a falling coconut than by a gamma-ray burst from WR104. This doesn't make for exciting headlines, but it's reassuring nonetheless. But WR104 isn't the only potential gamma-ray burst progenitor in the galaxy. There are roughly 500 known Wolf-Rayet stars in the Milky Way, and probably many more that haven't been catalogued. Any of them could, in principle, produce a gamma-ray burst when they die. The same is true of other types of massive stars that might collapse to form black holes under the right circumstances. And then there are the neutron star binaries, pairs of ultra-dense stellar remnants spiraling toward inevitable collision. We know of several dozen binary pulsars in the galaxy, and there are certainly many more that we haven't detected because their beams don't happen to sweep across Earth. Any of these systems could eventually produce a short gamma-ray burst when the neutron stars merge. The key question is, how often do dangerous gamma-ray bursts occur within range of Earth? This turns out to be surprisingly difficult to answer with precision because it depends on multiple uncertain factors. How many gamma-ray bursts occur per galaxy per unit time? What fraction of those are long bursts versus short bursts? How energetic is a typical burst? How narrow are the jets? What distance is actually dangerous for a given burst energy? Scientists have attempted to estimate these parameters using a combination of observational data and theoretical models, but the uncertainties are substantial. The most commonly cited figures suggest that a burst capable of causing significant ozone depletion occurs within the danger zone roughly once every few hundred million years. Some estimates are more optimistic, putting the rate at once per billion years. Others are more pessimistic, suggesting once per 100 million years or even more frequently. Let's take the middle ground and assume that dangerous bursts occur roughly once every 500 million years on average. Over the 4.5 billion years of Earth's history, that would imply roughly 9 such events. Most of these would have occurred before the evolution of complex life, when the biosphere was dominated by single-celled organisms that might have been more resilient to UV radiation. But some would have occurred during the Phanerozoic eon, the last 540 million years when complex multicellular life has flourished. The late Ordovician extinction, if it was indeed caused by a gamma-ray burst, would be one of these events. There may have been others that didn't leave clear evidence in the geological record, either because they were less severe or because the evidence has been erased by subsequent geological processes. Looking forward rather than backward, what does this rate imply for the future? If dangerous bursts occur once every 500 million years on average, the probability of one occurring in any given century is about 1 in 5 million. That's very small, but not zero. For comparison, the probability of a civilization-ending asteroid impact in any given century is estimated at roughly 1 in a million, which means gamma-ray bursts are perhaps 5 times less likely than asteroid impacts on a per-century basis. Both risks are dwarfed by more mundane threats like pandemics, nuclear war, and climate change, which have probabilities measured in percentages rather than parts per million. But gamma-ray bursts have one characteristic that sets them apart from these other existential risks. There is absolutely nothing we can do to prevent them or mitigate their immediate effects. We can deflect asteroids if we detect them early enough. We can reduce pandemic risk through public health measures. We can prevent nuclear war through diplomacy and arms control. We can address climate change by reducing greenhouse gas emissions. But a gamma-ray burst arrives at the speed of light, giving us zero warning and zero opportunity for defense. This fundamental helplessness is what makes gamma-ray bursts so philosophically unsettling, even if they are statistically unlikely. We're accustomed to thinking of ourselves as masters of our own destiny, at least to some degree. We can build shelters against storms, vaccinate against diseases, and develop technologies to address all manner of threats. But against a gamma-ray burst, all our cleverness and technology count for nothing. If one happens to be aimed at us from a sufficiently close distance, we simply lose. The game is over before we even know it's being played. This is a humbling realization for a species that often imagines itself to be the center of the universe. The cosmos is not designed with our survival in mind. It simply goes about its business, stars living and dying, neutron stars spiraling and merging, jets of relativistic material shooting across space, indifferent to whether any of these processes happen to intersect with inhabited planets. We exist in the gaps between catastrophes, in the intervals when nothing particularly destructive happens to be pointed in our direction. Our continued existence is not guaranteed by any cosmic principle. It's simply a matter of luck. This brings us to a broader question that gamma-ray bursts help illuminate. What is the long-term future of life on Earth, and what threats does it face from the cosmic environment? Gamma-ray bursts are perhaps the most dramatic example of an astronomical hazard, but they're not the only one. Nearby supernovae, even without gamma-ray bursts, could affect Earth through cosmic ray bombardment and increased UV radiation. Solar flares and coronal mass ejections can disrupt our technology and, in extreme cases, might affect the upper atmosphere. Asteroid and comet impacts remain an ever-present threat that we're only beginning to develop the capability to address. And on longer timescales, the evolution of the Sun itself will eventually render Earth uninhabitable, as our star gradually brightens over the next billion years and ultimately expands into a red giant that will engulf the inner planets. Against this backdrop of cosmic hazards, what can we do? The honest answer is not much, at least in the short term. We can continue to study gamma-ray bursts and other astronomical phenomena, improving our understanding of when and where they occur and what effects they would have on Earth. This knowledge won't prevent a burst from happening, but it might help us prepare for the aftermath if one does occur. We can develop technologies to monitor the space environment and provide early warning of solar storms and other more predictable threats. We can continue to search for and track near-Earth asteroids, developing the capability to deflect any that threaten impact. And we can think seriously about becoming a multiplanetary species, spreading human civilization beyond Earth so that no single catastrophe, whether cosmic or terrestrial, can wipe us out entirely. This last point deserves emphasis. As long as all of humanity exists on a single planet, we remain vulnerable to extinction from any event severe enough to render that planet uninhabitable. A gamma-ray burst, a massive asteroid impact, a supervolcanic eruption, a runaway greenhouse effect, even a self-inflicted catastrophe like nuclear war. Any of these could potentially end the human story if we have no backup. But if we establish self-sustaining colonies on other worlds, whether the Moon, Mars, the moons of Jupiter and Saturn, or eventually planets around other stars, we become much more resilient. A gamma-ray burst might devastate Earth, but if there are humans on Mars or in habitats throughout the asteroid belt, the species survives. Life goes on, even if one branch of it is pruned. This is not a new idea, of course. Science fiction writers have been imagining human expansion into space for over a century, and the space agencies of various nations have been working toward that goal, with varying degrees of commitment since the 1960s. But the progress has been frustratingly slow. More than 50 years after the Apollo moon landings, we have yet to establish a permanent human presence beyond low Earth orbit. The reasons for this are complex, involving political, economic, and technological factors that go far beyond the scope of this documentary. But the gamma-ray burst threat, along with other cosmic hazards, provides an additional argument for taking space settlement seriously. It's not just about adventure or scientific curiosity or national prestige. It's about the long-term survival of our species and everything we've created. Of course, even becoming a multiplanetary species wouldn't make us immune to gamma-ray bursts. A burst powerful enough to sterilize Earth might also affect Mars or other inner solar system bodies, depending on its energy and direction. To truly insulate ourselves from cosmic catastrophes, we would need to spread across interstellar distances, establishing colonies around other stars far enough away that no single event could affect them all. This is a project for millennia, not decades, and it's not clear whether we'll ever achieve it. But it represents a kind of ultimate insurance policy, a way of ensuring that the human story continues no matter what the universe throws at us. In the meantime, what can we say about the immediate threat from gamma-ray bursts? The bottom line is that the risk is real but small. There are no known gamma-ray burst progenitors close enough to Earth to pose an imminent danger. WR104, the most famous candidate, is almost certainly pointing away from us and may not produce a burst anyway. The handful of neutron star binaries in our galactic neighborhood are all far enough away and at safe enough orientations that we need not lose sleep over them. And the background rate of dangerous bursts from unknown sources is low enough that we're unlikely to experience one in the lifetime of our civilization, let alone our individual lifetimes. But unlikely is not the same as impossible. The universe has surprised us before, and it will surely surprise us again. The very existence of gamma-ray bursts was a surprise, discovered accidentally by satellites looking for Soviet nuclear tests. The boat, the brightest burst ever recorded, arrived without warning in October 2022. A 1 in 10,000 year event that happened to occur during our brief window of observation. If we've learned anything from the history of gamma-ray burst science, it's that the cosmos contains phenomena more extreme than we imagined, occurring in places and times we didn't expect. The prudent response is not to panic, but to remain vigilant, to continue studying these events and improving our understanding of them, and to take seriously the long-term project of making humanity resilient against cosmic catastrophes. There's also a philosophical dimension to all of this that's worth acknowledging. The fact that gamma-ray bursts exist, that they could potentially end life on Earth without warning, changes nothing about how we should live our daily lives. You shouldn't make different choices about your career, your relationships, or your retirement planning because of the minuscule chance that a gamma-ray burst might render all such planning irrelevant. The threat is too remote, too uncertain, and too beyond our control to be worth worrying about at an individual level. But at a civilizational level, it's a different story. As a species, we have a collective interest in surviving and flourishing over the long term, and that interest should inform our priorities and decisions. Investing in space exploration, developing the capability to detect and respond to cosmic threats, thinking seriously about how to establish sustainable human presence beyond Earth. These are projects that make sense regardless of the probability of any specific catastrophe, because they address the general vulnerability of having all our eggs in one planetary basket. The gamma-ray burst threat also offers a useful perspective on the other challenges we face. Climate change, nuclear weapons, pandemic diseases, artificial intelligence risks. These are serious problems that deserve serious attention. But they're also problems we have some ability to address through technology, policy, and collective action. A gamma-ray burst, by contrast, is completely beyond our control. We can't negotiate with collapsing stars or sign treaties with merging neutron stars. The contrast highlights how much agency we actually have over many of the threats we face, even when they seem overwhelming. If we can't do anything about gamma-ray bursts, we should focus our energy on the risks we can mitigate, working to ensure that our civilization survives long enough to face the cosmic challenges that may lie in our distant future. Let me close with a reflection on what gamma-ray bursts tell us about our place in the universe. We exist on a small rocky planet orbiting an ordinary star in the outskirts of a typical spiral galaxy, one of hundreds of billions of galaxies in the observable universe. For most of human history, we had no idea that the universe was so vast, or that it contained phenomena so violent and extreme. We imagined the heavens as a realm of perfect, unchanging spheres, designed for our benefit by a benevolent creator. The discovery of gamma-ray bursts, along with supernovae, black holes, colliding galaxies, and all the other violent phenomena of modern astrophysics, has shattered that comfortable illusion. The universe is not designed for us. It's a place of stunning beauty, but also terrifying violence, where stars explode, planets are sterilized, and entire galaxies collide over timescales that dwarf human comprehension. And yet, here we are. Against all odds, on this one small planet, matter has organized itself into structures capable of contemplating its own existence and the nature of the cosmos. We've built telescopes that can detect explosions billions of light years away. We've developed theories that explain how stars live and die, how elements are forged in cosmic furnaces, how life arose from chemistry and evolved into intelligence. We've sent spacecraft to every planet in our solar system and messages to the stars beyond. In the face of a universe that seems utterly indifferent to our existence, we've created meaning, beauty, knowledge, and love. That's not nothing. That's actually rather remarkable. The gamma-ray burst threat, in the end, is a reminder of both our vulnerability and our resilience. We're vulnerable because the universe contains forces vastly beyond our control, forces that could snuff out our civilization in an instant. We're resilient because, despite this vulnerability, we have survived and thrived for thousands of generations, building a global civilization capable of asking these cosmic questions and, perhaps, eventually, of answering them. The future is uncertain, as it always has been. We don't know whether a gamma-ray burst will ever strike Earth, or when, or with what consequences. But we know that life has persisted on this planet through countless challenges and catastrophes, adapting and evolving, and finding new ways to flourish. If a gamma-ray burst does come for us someday, it will find a species that has already survived ice ages, asteroid impacts, supervolcanic eruptions, and countless other trials. We may not be able to prevent the burst, but we might yet find ways to survive its aftermath, to rebuild and continue the human story in whatever diminished form remains. Or perhaps we'll be luckier. Perhaps the cosmic dice will continue to roll in our favor, sparing us from gamma-ray bursts for another few 100 million years, while we develop the technology to spread beyond Earth and insulate ourselves from such threats. Perhaps our descendants, living in habitats scattered across the galaxy, will look back on this era as the precarious beginning of a much grander adventure. A time when all of humanity existed on a single fragile world, ignorant of most of the dangers surrounding it. They might marvel at our courage or shake their heads at our foolishness, depending on their perspective. But they'll exist, which means we'll have succeeded in the most fundamental sense. The story will continue, even if we don't know how it ends. For now, all we can do is keep watching the sky, keep learning, keep building, and keep hoping. The universe may not care about us, but we care about ourselves and each other, and that has to be enough. Gamma-ray bursts are out there, exploding silently in the depths of space, briefly outshining entire galaxies before fading into darkness. Most of them will never affect us. A few might have shaped the history of life on Earth in ways we're only beginning to understand. And somewhere, somewhen, one might be forming right now that will eventually have our planet in its crosshairs. We can't prevent it. We can't predict it. We can only acknowledge it, learn from it, and get on with the business of living. The stars will go on exploding whether we worry about them or not. We might as well make the most of the time we have.